Okay, go to the first example. Yeah. So now, don't look at other things first. Look at the question first. A steel bar of cross-sectional area 200 millimeters square is loaded as shown in the figure. Okay, so find the change in length. That means the total change in length. That means the total deformation of the bar by taking Young's modulus as 200 gigapascal. So initially, we will start off with a very simple example. Okay, that is with two parts. Okay, with section A, section B, and section C, with two parts like this. Okay, and then when you take note, when you look at this question, you know, okay, the cross section is the same. Okay, no problem. Then you look, each section within the bar, okay, has forces. They have forces on it. So let's say this section here, you have 50 kilonewton. And at this section here, you have 20 kilonewton. And this section here, you have 30 kilonewton. So therefore, okay, to solve this problem here by using the normal method that we have used before is impossible. So that is why we need to apply the principle of superposition. We have to apply the principle of superposition. Okay, but before we apply principle of superposition, before we apply this, first thing you check, what is, now when you look at this question here, now what are the forces acting towards left? So left, you have this 50. Towards right, right hand side, so you see the arrow pointing towards right, you have the 20 and the 30. Now you check, okay, what are the total forces? Total now is it? Total is 50 towards the left. And what about towards the right? So you take 20 plus 30. So how much you have? 50 towards the right, 50 towards the left. So we can use principle of superposition because the bar here, this bar here is under equilibrium in a state of balance. Then when you apply the principle of superposition, okay, split the bar into two parts. Here you can see clearly that it consists of two parts. So split it up into two parts, AB and BC. Okay, follow? Two parts. So make sure that both the parts must be equilibrium. Now how? Now first you see this is 50. First you consider this bar here, okay? You have drawn this bar, but you don't know this is 50 and 50 or what you should put here yet. Now you see here, at the side here, at this section here is 50. So the purple section or the part, this part here, let's say we consider here is 50, okay? Because this is 50. So let's say we consider this as 50. So if this is 50, then you must draw another arrow, this section AB, section B here, in the opposite direction to this. This one, as section A, is pointing towards the left. So you must have another one that is this section B here on this part of the bar, pointing towards the right. So opposite direction, but equal magnitude. Okay, so this is 50, this must be 50. So this part here, purple color, this part here, now we say is equilibrium, 50 and 50. Left, and this is right. Okay, then when you have already considered this as 50, but then when you look back to the original bar, this is only 20. This is only 20. See the direction is towards the right, and it's only 20. But here, Because why this is 50? Because this is 50 I've taken from the beginning. So therefore, I must consider this as 50. But as compared this 50 here and this 20 here, that means there is an extra of 30 from here. That means there is an extra of 30 from here compared to this one only 20. So what you need to do is the next part, this blue color part, section BC, what you need to do is now, okay, since when you compare, okay, it's only 20 originally. Now I have 50 here. So how much I must remove from here? How much I must remove in order to get 20? How much I must remove to get 20? Why to get 20? Because the original is only 20 here. So how much I must remove to get 20? That is to remove 30 from here. How are we going to remove? Now, what we need to do is we need to take note of this arrow here. This arrow is towards the right because this arrow is towards the left. Okay, so now this arrow direction here and this arrow direction here is the same. But then this is 20, this is 50. So I must remove 30 from here. So remove 30 from here at the same section here, B, but at the second part, I must consider this line here, this arrow here, you see, opposite to this. We cannot consider this arrow acting towards right, towards the right. If we consider this arrow acting towards the right, same direction means plus. If different direction means minus. So I must minus 30 from here. So that is why I consider this arrow pointing opposite direction to this, 30. So that means I remove 30 from here. So for the equilibrium of this part, this is 30. Then I must consider this as 30 as well. See this arrow pointing towards the left. Then this arrow must be pointing towards the right. So this is 30. Okay. So once you have got this, now you can find the deformation of part 1, is part 1 here, plus the deformation of this part 2 here. Okay. So or we can straight away use this formula. This is deformation of part 1, which is force, length, area, Young's modulus for this, and force for part 2, length for the part 2 over the area and the E. Why the area and the E has been taken out from this thing here, this whole equation here? Why it has been extracted from here? Because the area is the same, the cross-sectional area of both the part is the same. So that is why I remove the A out, extract the A out here. Okay, then the Young's modulus. What happened to the Young's modulus? The question doesn't give us 2 or 3 different E. The question is only given one E, Young's modulus. That means you assume that this whole bar, steel bar, is of one material only, that is steel. That means AB and BC, they are made out of steel. So their Young's modulus is the same, 200. So that is why we say this E also is common for part 1 and part 2. So that is why we remove or we extract it out here like that. So the equation became like that. Okay. So now after that, you substitute your cross-sectional area, A, 200. Your Young's modulus, 200 GPa. Why is 10 power 3? Now, can you see this is mm squared. If GPa means it is in meter squared. So if I want to consider this to be into mm squared, so it should be kilonewton per millimeter squared. So this is actually equals to 200 kilonewton per millimeter squared. So you use 200, or otherwise you convert this to meter squared. This you convert to meter squared. So it should be 200 times 10 to the power of -6. 200 times 10 to the power of -6. Then you can straight away use this as 200 times 10 power 9. Okay, if you want to use in meter. Meter, convert this to meter. This should be 200 times 10 to the power of -6 meter square. And then this should be using this one, 200 times 10 power 9. Okay, if you want to keep it as millimeter, then this one also, then this one should be changed to millimeter square. So it should be 200 times 10 power 3. So put in your force here, 50 kilo. So make sure times 10 power 3. Then times with the length, that is 300 mm. If you are using meter, then this should be 0.3. Then plus this force here, 30, tensile, both cases tensile. So tensile I have to consider as positive. So tensile, so this is 30 times 10 power 3, because it's kilo. Then times with the length, 500 here. So you can find out the total deformation, 0.75 mm. Okay, now this is the first example.